that's fun. What do you guys say? Okay, that goes away. Okay, class, we're going to do 3.10. We're going to start example 1 again real quickly here, recording it for Lily and Emma, and then Luke as well. So let's see, you can kind of get the gist of what was going on here. So here's what we got. We are trying to figure out how to approximate a value. Sometimes it's kind of difficult to do on a calculator. Well, now that we have calculators, it's probably easier to do with calculator. But sometimes functions get so complex that we can't actually get the derivative formula for stuff. We can just approximate it. Good. So there's that little piece there that happens later on in calculus. And so, but we go from there. So here it is. Unless, well, Luke just needs to stare at the board and he gets all the information. So, but the rest of you guys can just chill as we have notes this from yesterday. So, also from Friday. Oh, by the way, no school Friday. We're good. Make sure you don't come here. No one else will be here. So let's go for it here. So here's my graph for it here. I have a line. That is the tangent line. It hits right at exactly one little spot right there. I'm going to call it A. So the value here is f of A. And ask me questions as we go. Sometimes it's good to see it the second time around, right? Okay, got that. Let's see what else. And then this is the line L of x. That's my tangent line at that particular spot. And then this guy is going to be y or f of x. Okay, everybody good there so far? Ask me questions as we go. And then we know this little equation from algebra. A long time ago, you know, that is true whenever you're trying to get an equation of a line. That's the equation we use. Okie dokie, let's plug in everything that we know. So what's my y1 value? Anybody? F of A. And then we're trying to get our slope. So the slope is technically this slope here. But as far as derivatives go, we have the derivative at A. Is that right? That would be the same thing as M. And then I got myself my x minus, and what's my x1? A. So now I have this. I can get the equation of my tangent line right away at one single instant. I just need to move f of A over. So this guy gets to go over to this side. I got y equals, there's my f of A, there's my plus of all the other stuff. Okay, talk to me, does that make sense? Okay, and then we're going to label our line. Instead of just a generic y, we're going to say that equation is of this line right here. It's L of x is equal to all that, and I know you have that in your notes. Except for Luke, because he's putting it into his memory bank. Seen it once, okay. All right, so what is this called? This is called the linear, what do we call this lesson? Linearization, is that right? Linearization. Okay, so different ways you can call it. You can call, sorry, Luke, go ahead, write it down if you need to. Tell me when you're done. Cool. All right, we call it linearization. This stuff we did not have in our notes last time here. Sometimes we call it the linear approximation. Sometimes it's called the tangent line approximation. So whatever it says on the homework, it really just means all the same thing on the notes. Cool. Okay. And let's jam. So first example here, this one you guys do have in your notes still. Find the linearization of that function there at x equals a, and we're going to use it to approximate 3.98, or the square root of 3.98. Now real quick here, if I stick a 1 in for x, is that pretty close to the square root of 3.98? Yeah. Yes. Except if I plug in a 1, 1 plus 3 is 4, and square root of 4 is 2, and that we know very easily, right? That's where the ease of linearization comes in. Okay, again, you guys have this on your notes, and so let's go with it. So L of x is that little nice formula right there. Now let's plug everything we need into that little formula. So let's go ln of x. What we need is, we need talk to me, f at what value? At 1, we good? Because that's what we're going to use for a. Then we need the derivative of my function at 1. And then we're going to go x minus 1 itself. We good? So that's the generic formula, or the approximation formula for the tangent line. Okay, I think I got everything I need. Now let's figure it out. You guys talk to me. What's this guy going to give us? 2. Yeah, we just talked about it. And then I'm going to use that one on the other slide here. So f of 1, plug a 1 into there. 1 plus 3 is 4. Square root of 4 is 2. And we've got our answer. Awesome. The derivative of that formula at 1. So here's my little problem. Can't do that directly. So I'm going to go like this first. I'm going to take, to do that, I have to do this first. Okay. So, okay, good there so far? Mr. Matterson, keeping up? Easy as pie, right? Yep. Okay. So the original function is the square root of x plus 3. And I'm going to rewrite it like this. Are we okay there? Cool. And the derivative is, anybody? 1/4, almost. Thank you. 1/2 in front. X plus 3. Perfect. Negative 1/2. And then if you want to, you could put a little 1. What's the 1 going to come from? The chain rule. It's the derivative of just the x plus 3. Perfect. Okay. Nicely written out. I got myself a 2 on the bottom, a square root of x plus 3 on the bottom. Every okay there? Ooh, that's the derivative, right? That gives me the slope at every single point along that graph. But I just want the slope at 1. So anybody with an answer for this guy? 1/4. That's what you were saying. Noah. That's what you were a step ahead. Yeah, no, actually you're like 14 steps ahead. Okay. So tell me if this makes sense. I got that. I got the 1/4. Now I can plug into this little formula. So this formula that I'm going to write is going to be specific to this problem, right? At a is equal to 1. So here's my rewritten. I think we have this on the notes. Tell me if you guys have it. So this one I rewrite as ln of x is equal to 2. Is that right? Plus 1/4 with an x minus 1. And then this one, just to simplify it, okay? The next one we won't simplify it because this trig gets complicated. But this one I'm going to simplify just a little more. How about 2? This will be x over 4. This will be a minus 1/4. And then that 2 changes into an 8 over 4. Voila. And I got myself, I think, let's see, the simplified version of it. Tell me if you guys agree or disagree. X plus 4 plus 7/4. Are we okay there? Okay, so now question, what in the world is this equation all about? And here's my little graphic for it. So here's my, I'm saying this. I'm saying right at about 1, when x is equal to 1, I'm saying that this line right here is very, very close to the blue line. Are we good? So instead of using the blue line and getting exact values there, I can actually use the pink line and get values there. So these two are pretty close, as long as I'm pretty close to x equals 1. Okay, good there. Sweet. Now I can do my problem. All that just to actually start the problem. So in order to get to 3.98, I'm already adding 3, so all I really have to do is add the 0.98 into my equation. All right, and then if you guys have a calculator, take them out. Just want to see this here. Cool, okay. So 7 plus 0.98 makes 7.98 over 4, and that is about, Noah, what'd you get? 1.995. Anybody check Noah? Not that he needs checking, but just in case. Just in case. Okay, cool. So again, we've made a linearization. We made a line, and lines are a lot simpler to plug in than big old humongous equations. Of course, this is an easy one. Later on in mathematics, they become humongous, right? That's why we do this. But real quick here, since you guys have a calculator, can you guys do this for me? Can we go back to the original problem and just plug in 0.98 into this problem right here, and I want to know, are we close? Did this linearization process get us close? Oh, yeah, okay. Again, check Noah. Yes, 1.994. That is pretty close. That is super close approximation. So we got tenths, hundred thousandths, almost like we're off by one digit in the 10,000ths place. That's pretty close. Okay, so let's do the same thing again in terms of a trig function. How about that? So this one, I think we started, we didn't finish here. So find the approximate value of cosine of 62 degrees. So we're going to get really, really close to a value that we know that's very close to 62 degrees is 60. That'd be cool there. Again, same exact process. I think you guys are starting to write down the notes now. Okay, so I'll slow down a bit. Oh, then we get to finally get to a physics problem. This was cool. Did you guys ever do approximate error in physics? Percent error in physics and stuff? Okay, cool. We'll do it from a calculus perspective. How about that? We'll see how that all works together. And then you guys tell me how Mrs. Blair did it as well. That'd be cool. Okay, so find the approximate value of cosine of 62 degrees using a is equal to 60. All exactly the same, right? What's our generic linearization function? X. Perfect. Okay, so then particularly to this problem, I got myself, you know what, we got to do this here. Oh, that's right. Guys, along our X and Y grid, right, our X's and Y's are real numbers, is that right? What are X's? Aren't they real numbers as well? Yeah, okay, so here it is. Here's my little problem. Even though it says 62 degrees, I have to convert everything into radian measurements. We're good? Because I got to be in terms of X's and Y's. So before we even begin, we have to convert to radian measurements, or else it does not work. All right, so let's go with 60 degrees. What's 60 degrees converted to radian measurement? Answer is pi over 3. Yep. We multiply, just in case we forgot from trig, multiply by pi over 180. The degree sign cancels, the zeros cancel. 6 over 18 is a 3, so how about a pi over 3? Ooh, the fun part then. What's 62 degrees? We just might know in the next minute and a half. We'll just have to wait for Luke. Oh, no, I knew the exact answer. Oh, no. I think it might have been on your notes. Okay. I can start singing Jeopardy. Dun, 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 dun. Dun, 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 dun.
Really, it only simplifies down to like 31 pi over 90.
Yep, I go with that here. So let's see. We've got a pi over here, now 180 down here. The degrees cancel, and I take half. Is that right? Because they're both even numbers. Half of 62 is 31, and half of that's 90. Yeah, not very nice, but it is simplified. 31 pi over 90. Okay, so I got that. I got it, everything in terms of real numbers now. Now I got this stuff to plug in. So 60 degrees, same thing as pi over 3. Can you guys change this equation to specific to this problem. So all the A's turn into pi over 3s. How about that? I'll let you guys do that first. Go ahead, see how you guys doing. Walk around a little bit here. So just changing the A into pi over 3.
And the function that f is just constant, right?
Yeah. Yeah. So let's go with that thing. All of you guys have it now here, so I'm gonna write it up. So this guy now is f of pi over 3 plus the derivative at pi over 3 x minus pi over 3. So let's go with it here. So I need to know, anybody tell me what is cosine of pi over 3 exact value? 1/2 is good by me. Okay. Now I need to know the derivative of that at pi over 3. So again, what do we got to do first? Perfect. Yeah, the derivative of cosine is negative sine. Perfect. And then we're going to plug in our value. You guys are ahead of me, so let me catch up here. Plugging in a pi over 3 into negative sine, which is the derivative. I get myself a root 3 over 2 with a negative in front. Okay, I think we're good. So now, can you write the generic equation specific to this problem and specific to A is equal to pi over 3? Isn't it funny in mathematics? A lot of it is just substitution, right? You put things together and like, okay, if this means this, if this equals that, then that equals that. All right, and don't simplify it out because again, you got square roots in here as well. Just I needed the 1/2 minus root 3 over 2. How about x minus pi over 3? Right? Once you start, you could if you wanted to, like we did in the last one. But why do it if we don't really need to anyways, right? Okay, what we do need to do is plug in our value. So this is the linearization, right? This is the approximate line that approximates the value. So we're trying to get to 62 degrees. And the value is 31 pi over 90. So all yours, 31 pi over 90, and all yours to finish up. So I need the exact answer first, and then once you get to the exact answer, then give me the approximation. So this one doesn't matter because you're not taking a trig function. Right? There's no trig function to be taken. So let me plug it in. So that's a 1/2. It's a root 3 over 2, and this guy's going to be 31 pi over 90 minus. Oh, that's so cool. Yeah. So the pi over 3 becomes what? 30 pi over 90, right? Subtracting that out should give you. So I'm going to write it in just for completion's sake, even though you guys skipped this step in your minds and already got to the next one. That's cool. I got myself a pi over 90. Just simplify that. Let's see. Write it underneath the same denominator. So I got myself, looks like a 180 denominator on that side. All right, need common denominators, what I got here. Good, Joe. walk around here and then put this together as one term, because now you're looking at two terms here, right? So normally in mathematics, you would write it like this. You'd write it as 90 minus pi root 3 over 180. All right, let's go with it. So, let's see, I'm going to take that guy and let's approximate it now. So 90 minus pi root 3 over 180. Let me write it on the next slide because I'm running out of space. And Elke, you done with this one? Okay. So I'm going to move this up to the front. This is fun. So I had this fun. I was going to go all crazy, Mr. Matterson, just kind of make it all go all out, but I decided not to. I decided just to. Oh, hold on, did it move? Hold on, I don't want it to move. Move. Nope. Hold on, let's try it again. Oh, see, effect has been spoiled. It just jumps to here. Never mind. The cool stuff is not there. Okay, you guys on the calculator, give me the approximation. 0.46977 according to Noah. Okay. Cool. And then, pretty close approximation? I don't know. We'll see. What's cosine on, according to your calculator, cosine of 60 degrees. Now you need to be in degree mode. So cosine of 62 degrees is? Perfect. 46947 or something like that.
Yeah.
Mm-hmm. No problem. Good. Yep. Please get your questions answered before you leave. Okay, are we good, guys? So we have made simpler functions in order to approximate different functions here. Where is this used at? Yes, it's used in physics. In physics, we call it differentials. What's your physics teacher name? Ms. Bear, there you go. Yeah, somebody thought it was an L and stuff. Yeah, Ms. Bear. Did Ms. Bear ever talk to you guys about differentials? Heard the term maybe? Okay. And are all you guys in physics? No. Elka, are you? No. Okay. Anatomy. Okay. Gotcha. Okay. No problem. So let's go with it here. So let's set it up all the way from the beginning. So thinking caps on. I want to actually develop it with you guys because this is kind of cool to see. So you guys talk to me here. So if I start off with this right here, again, this is so cool. You start off just playing with notation and it kind of gets you somewhere. That's what happens here. When Einstein, when he invented relativity, part of the process was he was just playing with notation. They're like, hey, if this equals that, well, hold on, what? And so he goes into this whole discussion about just notation giving us some answers here. So can you please, for me, can you guys take the derivative of both sides? Well, hold on. With respect, what's our function in? What's the variable of our function? It's x, huh? Because we have fx. Thank you. dy over dx equals, and then we can write the notation for here. We've been doing that a lot, is that right? So now the question is this. Fine and dandy. Well, what if instead of dy and dx just being some notation that we use, what if they were, and what, hold on, what about if they were quantities? And if they are quantities, what do they measure? We good? That's the question. Boom, we got level 8 on our hands. Are we good? So if dy dx wasn't just notation, remember how we just use it as notation? The question kind of flips and says, what if dy dx were values? And what would they actually measure if they were values? Let's take a look at it. First things first, how about this? If they are values, can I multiply by dx on both sides? Yes, I'm going to multiply dx on both sides. And I have an equation that says this. And let the party begin. We good? Okay, keep that in your mind. dy is the same thing as the derivative of f at x times dx. Cool. Okay, next. Let's do this here. This one, maybe just kind of think with me for a little bit. Let me do an illustration here. So let's go with this. Let's say I have this little function. Let's say it's x squared. Again, don't write stuff down. Just kind of think with me here. Tell me, derivative of that guy is 2x. Awesome. Okay, I go with that. Okay, so then the question is this. If I were to take, and I would just say, okay, dx is 1. Again, just trying to figure out what this means. Hold on. Isn't dx really the difference along the x-axis? Right, it's the change in, right? It's the change in x, is that right? Okay, so if I'm going to use this, let me just do an example. I'm going to use 1 as my target, and I'm going to go 1 away from my target. We good? So x is equal to 1. So according to my formula, let's see if this makes sense here. So dy is going to be, what's the derivative? I should have plugged in the 1 here. So everybody okay there? I'm going to plug in a 1 into here. Is that right? Since I'm using 1 as my value. And what's my dx? 1. So I got myself a value of 2. Like, what in the world does that mean in terms of a graph? We're good? So let's take a look at it. So if I have my x squared, my beginning value is 1. So I'm like right here. Everybody okay there? Here's my 1. How far am I trying to go away from 1? 1 value. I'm going to go from here to here. That's what I'm trying to do. And somehow this value is 2. Like, so the question is, what in the world does this 2 mean? And so if I put my little linearization graph on here, are we okay there? So here's what I got. My dx, as I move 1 away from here, it just means the difference along my y value is going to be 2. So where did I get to? I got to 3, and I got to my linearization line. Are we good? Okay, so keep that in your minds. Okay, that's kind of important right there. So dy actually is a value, dx actually is a value, and dy is the change in whatever your derivative is. Are we good there? And since derivatives are lines, that actually is just going to be your slope of your line. Okay, we good still in mind? Let's jump to the other side. So tell me, let's go all the way back to algebra. And we're going to put both these concepts together. Okay? So m is your slope formula from geometry, right? It's the change in y over change in x. Anybody know the little symbol that we use for change in? Delta. It's a little triangle. That's right. So this guy would become delta y over delta x, just a little faster way of writing it. And what's my slope formula from algebra 1 for slope? Something like y2. Perfecto. Okay, so now let's do a little bit of work with this one here. And again, just thinking about it. If these guys were functions, tell me if you guys agree with this still here. These were functions, I'm thinking this. I'm thinking f of x2. Agree or disagree? Yeah. Minus f of x1 over. Perfect. Okay, so I got that. Okay, so I'm good there. So now let's draw a little diagram. Some people are copying it down. Wait a little bit here. Again, sorry guys, a little bit of a long haul here. And then we're kind of put it all together because this is the whole concept of air and percentage air and differentials all coming in from calculus. Okay, diagram, ready? Diagram looks like this. If I have a graph, looks like that. And my first point, I call it P, and this is going to be x1. Everything there. This is going to be f of x1. My second point over here, it's going to be Q, and it'll be x2. And it's a little bit higher. Right there. Are we good there so far? So that's the algebra approach, right? So now, since we know how to do calculus, let's go for it here. So let you guys catch up, drawing it out. So here's what I'm gonna do. I'm gonna take this little guy right here. I'm just gonna call it X. That's my starting point. And instead of having an X1 and a Y1, all I'm gonna do is I'm gonna say, this is how much I'm gonna move. I'm gonna move from here, and I'm gonna move delta X. Are we good? We're gonna just change up this value here. Again, ask me questions as we go. So you guys talk to me. What is the value right here then? What's the value of X2? And we can even forget the 1, right? We're just starting with the generic X. Doesn't matter where you start, as long as we start with some kind of X, and then we're going to move forward. So, Elka, all yours again? Perfecto. Okay. Love it. Okay, we got this. This is the end right here. Look at this. I'm going to start off, instead of having a specific X1, I'm going to write a generic X. Doesn't matter where I start. Who cares? We good? And then for f of X2, that's going to be a function, which is I'm just adding a delta X to it. So now, instead of having specific points, I can go anywhere with this. Is that right? As long as I know my X value, and as long as I state how much I want to move delta X. But hold on. Wasn't delta X part of a formula in the beginning? Okay, so let's see this here. See if this makes sense. Go back to our little sheet. Remember this little guy right here. We did all this, blah, 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 right? Blah, 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 blah. And now we get to the real blah, blah, blah right here. Let's see if this makes sense. This now f of X2 now is X plus delta X. And this is f of X over what? Perfect. Okay, let's simplify this just a little bit more. So on top, that has to stay the same. What's on the bottom? Just delta X. Okay. Sorry guys, that was a long process here. A lot of abstract thought here. So real quick here, this little delta X here and that little delta X, aren't those the same thing? Yeah, so we don't care about that. Let's just write our numerator. That little delta Y is equal to what? Perfect. Here's our formula. That's the one we want. Right there. You want to write that one down? Go for it. And then we'll put it all together here. Then we'll. Sorry guys, a lot of abstract thought, but I want us to sort of think through that, okay? Don't want to just give you guys a formula that says, here's your formula. Where'd the formula come from? And Mr. Matters, I just want to say, these kids are awesome. We're doing 300 years of calculus in 1 year. That's how awesome we are. Okay, so according to x squared, and we have 2 people that almost got their PhD. They're like so close. They're like right there, like, oh shucks, someone did it before. They're like, oh shucks, someone did it before. Okay. Skip college. A long, long time ago, got to tell you a story now. There was people used to go to college when they were like, 14 or something, sometimes, right? So this person that studied ancient ancient Egyptian hieroglyphics, he gives a talk, and this is his presentation to enter the university, right? And I believe he's 14. He's studying ancient hieroglyphics from the time he was like 6, So as he's doing it, he's making all these discoveries as he go, right? So then at age 14, he writes this paper, and if it's good enough, he gets to go to the university. So he brings it in front of the board and it's actually an open meeting, so there's public can be there as well. The professors of the university are there, right? And then they're judging who can get the scholarship and who can get. So he starts presenting the information, just goes. And then the professors find out This is new information, never done before, original research, and they give them a degree right then and there. Like, forget the 4 years, here's your degree. So, yes, it has been done before, guys. So shoot for that. He sat there, nothing else to do but look at ancient hieroglyphics. Yeah. Okay, so now the question is this. So dy, remember that from our first graph? Dy was the up, it was up to our linearization line, right? What is delta y? So let's take a look at what is delta y. So same exact function. I got x squared on my hands. And x is 1, is that right? So dy, dx would be what? It would be f of, tell me, okay, f of 1 plus 1, is that right? We start off with 1, right? And then we're going to head off 1 more. That's what that, and yep, I think Joe's getting it here. This is x squared, is that right? This is the function, and this is the function. So this guy gets us 4 minus 1. Where in the world do we get 3? What does 3 have to do with our graph? Anybody? Oh yeah, so very close. Yeah, Joe's close. He's saying that that's the 3, but remember, this guy's not talking about value, right? This is talking about the difference in values. Where's the difference in values? Perfect. Okay, so here it is, guys. Joe got it right on. There's the difference in x. We went a difference of 1, and then we went up 3, right? So the delta y really gives us the exact value of our function. Dy gives us the approximation to our linearization line. We're good? And that little difference right here, that is called, anybody? 5-letter word, starts with an E, ends in air. Ends in R. And there's a RRO in the middle. Thank you. Yes, air. So our air is this one right here. We good? Here's our problem. Here's where we get not the correct values, right? This is the actual answer. This is our approximate answer, right? There's our air. Whew. Okay, so look at this. This is kind of interesting too. So we can actually be under, right? Remember this was 2, right? Dy was 2, but delta y is 3. We can go the opposite way. We can have, if it's bending this way, dy is going to be smaller than, dy is going to be bigger than delta y. Okay, so let's go for it. Let's go to the one that we did not do yet. Exercise 3, let's go for it. So we're going to do this, compare the values of delta y and dy. And let's give it a function here. Function is that little guy right there. All right, it next changes from 2, and let's not go to 3. Let's go to something super, super close, because that's the whole point of approximations. Cool. Okay, so I'm going to be 5/100ths off. And I want to see, first of all, is there error from my approximation to my exact value, and how much? We're just practicing to plug in. We're just plugging. Let's see. We're just plugging in just to practice plugging into the values here. So first things first is delta y. Formula for delta y? Oh, perfect. Yeah. So this is f of x plus delta x. 2.05. That's the value minus the original one, which is f of 2. So this would be the change from 2, right, to the next value up.
And then that's over the delta of x, which is 0.05.
One second. I'll go ahead first.
Sorry, so delta x would be 0.05, right?
Yeah, delta x is 0.05.
So
Yep, let's do that on the board. Just clarify, yeah, thank you all so much. And then I'll give you a question here. So delta x is 0.005, right? That's how much we're scooting across away from the 2. Okay, and Hawkins, your question? I got it. Okay. Boom. So can you guys plug, I'll let you guys plug it in the calculator, go for it. Can you plug in 2.05 into that function? It's going to be 9 point something or other. Cool, okay. Joe got it. Okay, 9.717, and I put a whole bunch more in there just to make sure. How about just the 2? 9. So it looks like we went up how much? What, 7-ish, yeah, 717-ish, 718. I just kind of put in the extra values just to sort of see it. Okay, so this guy tells the actual distance from the y value at 2 to the y value 2.05 is a 0.717625. Now the question is this, what's my quick answer? What's my dy answer? So the formula for it is the derivative, is right? What's the derivative of f of x? 3x? Perfect, and then I have a dx next to it, right? Which is 0.05, we just figured out. Oh, and let's do this one here on the board. So we remember along our x value, the delta x and the dx are the same, is that right? So that is the same thing as always. Okay, you guys plug in a, what do we plug in?
And why is that at the end? Well, I get that it's
dx or delta x means the same thing, right? Along the y, along the x-axis.
no, yeah, but why was it at the end of
Oh, yeah. Sure, absolutely. This is cool. This is why. So when we have this function only, and we take the derivative, right? We think of this as only notation, right? And then we switch our minds to say, hold on, what if they were values, right? If they were values, then I have myself that right there, right? Yeah. It's this whole concept of as you look at something, right? Like definition of genius, right? Genius looks at something and sees something different, right, than all the others. And that was this whole point here. Instead of seeing it as notation, you see it as, oh, what if these are values? What are they then? Okay, we are going to plug in a what into this? We're plugging a 2. Absolutely. 2 times 2 squared, or squared is 4, 12. 16 minus 2. Perfect answer is 0.07. Cool. Pretty close? I think so. Yeah, 0.7. And again, pretty close? Absolutely. That is a pretty close statement. So we're off by a 100th, right? Closer to 200ths, yeah. Closer to 100ths. To be technical. Cool. Okay. Okay. That's cool. So that is, again, that's the differentials, or we just call it air between the actual and as well as the approximation. So let's go with it. So exercise 4. Here it is. Let's go. The radius of a sphere is 50 inches. With a possible error of plus or minus 0.02. So this is the maximum error. And this is the radius, if you want to put in the radius. Put all this here. Let's let you guys write that out. Go for it. So I got a sphere. It has a radius of 50 inches. And in physics, right, we got to measure stuff, right? So we have some kind of mechanism that can measure up. And then we have a possible error of 0.02 inches. Pretty precise, right? 100th of an inch, right? Or 200ths of an inch error. We're going to figure out what's the possible error that we have for the volume itself. How much error do we have? And then what's the percent error as well? So let's see, just in terms of inches themselves, I want to see how much error we have. Huh, did I not do it? I think I did it. Oh yeah, I did. Okay, cool. Okay, let's go with it. A little graphic here. Don't need to write it down, but just kind of think with me here. So I have a radius, x value, right, and a volume for my y value. I'm somewhere around 50 inches. And I notice I have an error of 0.02 to the right or a 0.02 to the left. So what, my radius could fluctuate, is that right? 50.02 or a 49.98, is that right? So now I need to figure out how much air is there in the volume itself. And I think it'll kind of be surprising here. So here's my 50 exact answer, but then I also have that air right there, right? It's gonna be some air. Well, I know how to calculate air. Let's see. If my volume for my sphere is 4/3 pi r cubed, what's my derivative? Four pi r squared. Awesome. And now we know dr, not just notation. Dr are their values, is that right? So check this out. If I multiply both sides by dr, notice what it tells me. It tells me my change in volume, is that right? My change in volume is going to be that formula times my change or error in my radius. Are we good? That is so cool. So changing the fluctuations actually in my volume are going to be determined by my fluctuations of my radius, multiplied by that right there. Okay, let's plug in some values here. Let's see, my radius is 50, is that right? And my error is 0.02 plus or minus, right? It can go either direction. So tell me when you plug it in, tell me what your answer is. Obviously, if you plug in a positive 0.02 and a negative 0.02, we just need to put a plus and minus at the end of our answer. Doesn't matter because you're not using a trig function. Only time it matters if you're using a trig function. That's what I think so too. So if we have a plus or minus, right, we don't really need to compute plus or minus. You're going to get the same answer. Is that right? So here it is. Yep. And Hawkins got it right. And Joe got it right. It is pretty big. I think in my mind, look at this. If we plug in a 50 in here, you square it, times the plus or minus that, we get ourselves 628. So, yeah, and where did the cubic inches come from? It came from two of them being here, is that right? And then one of them here, because there's inches right here, right? So inch squared times inch makes inches. Guys, that's a lot, isn't it? 628 inches. What is? How many feet is that? We're off. And hold on, but our instrument was. Boom.
52.359.
From memory, from calculation. That is big, humongous volume. Isn't that a big volume change? Right? It wasn't like 3 inches, right? It's 628 inches. Okay, so what? Like, can we even trust physics at this point? It's all fake. Okay, let's see. Well, here's my only little thing. Converting it into feet, guys, real quick here. Do you guys remember it from physics? Is you can't convert a cubic value, right, by a linear value. Do you guys remember that in physics? Hopefully you guys studied that in physics, right? So if you have area squared and you're trying to get feet squared, you got to go by not 12, but 12 times 12. Does that make sense? Right? So there's one piece. So you just can't divide this by 12 and call it feet. We're good, Hawker? Does that make sense? Yeah. Okay. Second of all is this. Guys, we're at 50 inches already, right? 50 inches is what, almost 4 feet, is that right? We got a sphere that's almost 4 feet wide. It's this wide right here, right? And we're computing volume of this, right? So now the question is it percentage wise? Is it a big amount or is it a small amount? That's my question, right? Because that's what matters, right? If you have a small amount, if you're dealing with a half an inch and you have an error of 628 inches, you're in trouble, right? But if you're dealing with 10 million inches and then you get an error of 628 inches, is that a lot? No, very, very small. So now we got to do is we got to compute the relative error. So relative error is the error compared to the size that you have already. So this one, not going to give you the setup for it, just the formula. Here's your formula. All right, based upon the formula. Ooh, I got a delta V on my hands now here. So you guys think about it here first. Try it yourself first. Set up the formula first, and then see if you. What is delta V? And let's see. This makes sense, guys. I can go back to the original problem. Is that right? Or what's my approximation? My approximation is delta. Is that one right here? We good? Right, because I'm super close, right? As long as I'm close, right? I can substitute the y values, delta y and dy as being pretty similar. Okay, so anybody give a formula for delta v? Perfect, awesome. And then the volume formula. Q, perfect, okay. And can we plug in let's simplify this out first here. Can we just multiply by 3 on both sides? Just to get rid of that, don't like that thing on the bottom here. 3's cancel. I'm left with 12 on top, 12 pi r squared dr over 4 pi r cubed. Can I reduce this any more? Yeah, the 12 and the 4 reduced. That's a 3 now. That's cool. The pi's are gone as well. Is that right? And I have an r where? On the bottom. I got air. Okay, in my denominator. And then I got my dr, which is is a multiplier. I could stick it at the end. I can stick it in front. Okay, let's plug in what we know. What are we plugging in for dr? 0.02. Yeah, and R 50. You got it. Okay, so 3 times this guy divided by 50. What do we got for that answer? 0.0012. Interesting. Okay, that is relative error. So what I want now is a percent. What's my percentage of error? Cool. So sorry guys, right here. And then we got ourselves percentage. Sorry, did we go back? Back here. Let you guys time to write it down. Go for it. Okay, let's go with it. Percentage error. Percentage error is
I go for like 50%.
uh-huh.
I'll take anything
In error.
in the store.
It's 4. Okay, so 628 inches cubed, according to this, because we have a 50-inch radius, right? Really, it's not even like barely above a 10th percent of an error, right? That's what we have relative to that. So yeah, I can live with that, right? 1/10 of a percent of error with that. Okay, guys, what do you guys say? Any comments, questions, anything that we've good? You guys talk to me. How did you guys do percent error in physics? Just out of curiosity here. How did you guys calculate it ever? Or? Okay, so yeah, going back to here. Yeah, this. Yeah, so this is your experimental value, right? And then this is the theoretical value, right? And then you have, and then times 100 to give you your percent. Okay, cool. And then how do you guys do your experimental value? Do you like, is it by measuring something with a ruler or?
Yeah, that's what we actually measure,
How interesting.
Yeah.
Okay. Uh-huh. Oh, ouch. Okay. Okay. Lowest percent error you guys had in physics class? What were you guys measuring? Oh, that's funny. Okay. Uh-huh. Gotcha. Okay. Uh-huh. Sweet. That is awesome. Okay. Cool. Okay, so there it is. There's air and how we calculate it. All right. Your homework is right over here. You guys can write it down. So this is 4 problems only. So number 1 and 2 right here. Sorry, numbers 1 and 3 are going to be very similar to exercise 1 that we did. 23, I'm going to give it to you guys slightly different. You guys should be able to figure it out. There's going to be like, oh, this is that kind of like the extension question. If you figure this out, um, you've thought through and you've understood what we're trying to do. You're going to estimate an exponential function. Okay, and then 35 is going to be something like we did with the sphere, except it's going to be a rectangle, and you're going to talk about area at that point, again, as opposed to a sphere and talking about volume. So very, very similar to that. Yes, until you find yours at home, wherever it's at. Uh-huh. Uh-huh.
And then one thing just fell out of Joe's back.
Yeah, that's funny.
Oh, sure.
Right, yeah.
You didn't notice. Y'all know you're Joe.
He was just pulling out a calculator from his backpack. Didn't realize he was pulling out two different calculators until both of them fell out. Both of them fell out. All right, guys. And with 45 seconds to go, we're all good to go here. So.